Good. Should I?
That's fine. Yes.
Um, Hi everyone, welcome back after the break. Yes, it's on. Yeah, okay. Yeah, welcome back after the break. Let's just settle in. Yeah, we are running like 7 minutes late, but okay. So the next speaker is Sumegha Garg. Coincidentally, she also did her undergrad in IIT Delhi. Yeah, so she did her PhD in Princeton, then was a postdoc at Harvard. Currently is a professor at Rutgers University. She has a lot of exciting work about interactions of randomness and computation. And today she'll be talking about the coin problem.
Yeah, thank you for the introduction, and I'm very excited to be here and part of the celebration. Today, I'll be talking about recent works in my recent works in the coin problem and understanding how programs can solve the coin problem. This talk is based on joint works with Mark, Yan, Shuo, David, or and Jiapeng. Feel free to ask me questions in the middle. I'll be very happy to answer any clarification questions in the middle. Okay. No, this is not.
I think probably not selected.
Okay. So what is the coin problem? It's a very simple problem. You are given a biased coin which is biased towards either heads or tail, and you want to figure out which way the coin is biased using independent coin tosses. So let's quantify it a bit. You have a biased coin which has bias delta. Delta is a parameter that we will keep changing during the talk. And this coin is biased either towards heads with probability half plus delta, that is, it would be heads with probability half plus delta and tails with probability half minus delta, or it is tails with a larger probability, which is half plus delta. And then we want to figure out which way the coin is biased using using independent coin tosses, which is the number of tosses is n, and the probability that with which we want to solve this problem is 0.9. So this is the problem. This is like a very fundamental problem in statistics. You are, or in any measurement. If you want to in any estimation task where we want to figure out like the mean or something which way the coin is biased, and this fact that you require 1 by delta square tosses to distinguish between these two cases, that distinguish between the case where whether it is biased towards head and versus whether it is biased towards tails, you need at least 1 by delta square tosses. If you have less than these many tosses, you cannot even it is impossible to distinguish or solve the coin problem. So this fact has been very useful in various areas of statistics, for example, to prove tightness of Chernoff bound or to show various information bounds that you need these many samples to detect certain things about a distribution. Yeah.
So what does it say if delta is 0? In other words, a fair coin? Just curious because it's too strange.
So if delta is 0, then the coin problem is not well defined. Like there's no distinguish. Yeah.
So, but we cannot. Does that also translate to we cannot recognize a fair coin with any reasonable number of tries?
No, it means that if you're given a fair coin versus a fair coin, you cannot distinguish between them. Yeah. Okay. So, but statistical indistinguishability does not imply computational indistinguishability. Like if it is possible to distinguish, that does not mean that with the computational resources that we have, we can distinguish them. So this, because of this, there has been a lot of work in computational complexity theory to understand the hardness of the coin problem for various computation models. So especially like for computational models where you cannot compute majority, it has been very useful to understand whether those computational models can solve the coin problem or not. So some of the examples of these computational models where the coin problem has been studied is small depth circuits, restricted branching programs, and streaming and online learning algorithms. So, for example, one of the works under small depth circuits, a recent work showed by Newton and all showed that for example, for AC small depth AC0 circuits, these are circuits with parity gates. These are circuits which we think cannot compute majority. This coin problem was used to prove a depth hierarchy theorem. So the understanding the hardness of the coin problem has been central to understanding various computational models, especially in the circuit complexity in the recent past. And so in this talk, we will be focusing on read-once branching programs. I will first define what are the read-once branching programs, and then we will see what the question we ask is like how much width is required to solve the coin problem. So we will talk about like what do we mean by a width of read-once branching program, but the computational resource we care about is width. So we are given n process and we want to figure out if it is biased towards heads or tails using as low width as possible. And we will see what has been recent research in proving tight width bounds for solving the coin problem in read-once branching programs. So we will look into details of an upper bound construction, that is give a read-once branching program that solves the coin problem. And then finally, I want to mention very briefly the recent results in multi-pass branching programs and end with the open problem in this direction. Okay, so let's start with what is a read-once branching program. A read-once branching program is a non-uniform model of computation where now your computation is represented by an acyclic directed graph where there are W times n nodes, that is the computation is divided into n layers and each layer contains W nodes, and these node represents the state of the algorithm in this layer. And so how do you do computation here? You start, so for every node in this graph, there are two edges going to the next layer labeled by 0 and 1, and then so for all these nodes there are some edges going, like there's a 0 going here, there's a 1 going here, and so on. And then how do you represent a computation is by saying that you start from a start vertex, which is in the first layer. You read the input bits one by one, x1, x2, xn, and then finally reach a vertex in the last layer. And then if you reach a green vertex, that means that you are supposed to accept this input. If you reach both of them are green, a dark green vertex, if you do not reach this special vertex, then you reject this input stream. And this is called read once because you're reading the the entire input x1 to xn only once, going from left to right. Any questions on the? So yeah, so these are we don't care about it.
Only the first layer is what I understood.
No. So you start from the this start vertex, and then you can go on, like let's say you get a 1, and then maybe you get like another 1 or like 0.
Again, the coin, the random choice.
I'm saying that okay, so this computation is defined for every input stream, for every input, an n-bit input. So for every n-bit input, there is a path in this read-once branching program that will take you from start vertex to the vertex in the last layer. And then if if that path reaches this dark green vertex, then you accept that input.
0 and 1 are the coin outcomes.
0 and 1 are input bit. Now, if I will talk about, when I will talk about de-advanced branching problem for the coin problem, then we will think of 1 as the head and 0 as the tails.
W is smaller, then at some point you may hit the 1 and there will be only one choice.
No, so you might go there like this. It can be these edges can be in any order, right? Like it's not that with 1 you are always going down. It can be, yeah, it can be at any, yeah, go to any vertex in the layer, yeah. Yeah, it's yeah. So this is oblivious read-once branching program. So the input bit is fixed, x1, x2, and xn. No, so this is like I am reading, and if that input bit is 1, I make this edge transition. If that input is 0, I make this transition. There is no probability associated. It's a deterministic computation that I can do on every input stream, every input, n-bit input. Okay, so to connect it with the computational models that we all know, which is Turing machine, I want to say that a space S algorithm that goes over the input once. So it's not like it cannot go over the input many times. That goes over the input once can be represented in the same order, can be represented by a width 2 to the S read-once branching program. So this is how you connect memory to the width of the branching program. This is because when we are doing this, so if you have an algorithm that uses only memory of S bits, there are 2 to the order S different configurations of your Turing machine, and these configurations can be represented by the nodes in a layer, and then you make the, so after you read an input bit, you change your memory configuration from one to another, and that is exactly represented by the edge that is the from one layer to the next layer. So so this is to say that, like, in this talk I'll be only talking about the width of read-once branching programs, but these results also give interesting bounds for the memory load bounds for just like uniform model of computation, which is the Turing model. But in the Turing machine, so the Turing machine model is usually the uniform model, whereas this is a non-uniform model, which that I mean that if it is a uniform model, then all the layers would be the same. But here you can, depending on the ith layer can be what I mean by this, like the transition from ith layer to I plus 1th layer can be different from the transition from I minus 1th layer to ith layer. So this is what it gives the non-uniformity. And for Turing machine models, constant space algorithms are usually not interesting, because that means that you have only like constant different configurations, and you cannot even read the input. But in the read-once branching program, constant width branching programs are also interesting, and people have been studying for a long time what are the capacities of constant width branching programs. Okay. So, so this is read-once branching program, and only in this talk I mentioned a space S algorithm. From now on, I will only talk about branching programs. Yeah. So the deterministic finite automata is it's not equivalent, because so you can think of deterministic finite automata is also all the layers are same. So if I am looking at a deterministic finite automata, that means that all the states are represented in the first layer, and then the transition function from the first layer to the second layer is same as the transition function from the second layer to the third layer. Because it's an automata, the state transition is defined. But here, your transitions can differ as you're reading each bit. The transition when you're reading the second bit can be different as from the transition that you're reading when you're reading the first bit, which is not the case in automata. So it's strictly stronger model of computation than automata. Yeah, so there are W states, like we will be like, okay, this is the ith state of the jth layer. That's the how would you call it. Okay, so what's a multipass branching program? The multipass branching program is you have this first layer, and again you can read the input again. Basically, this gives us like there are transitions again while reading the input the second time. So these transitions in the first part of the branching program can be different from the transition in the second part, but you're reading the input twice, and then you're making these transitions, and now the final accept state is after reading the input two times.
Second, what should I call it? This second WN grid is the same as the.
It's not the same. It can be arbitrarily different.
Some different kinds of things, right?
Yeah.
There's the order.
The order has to be. So that's why it's called the pass. It's a multi-pass. You can also define read twice. Read twice is like in each path you are reading each bit at most twice, and the order can be different. But this is just multi-pass. You're making multiple passes. Okay. So this is about the definition of read once branching program. We will.
Can be arbitrarily different. Then how is this? How many times are we allowed to, get back to the second layer? This one.
Yeah. So if you have if you are considering two pass branching programs, then you will do twice. If you are considering 3 times, then there would be another 3 pass, and so on. So it depends on like the number of passes you are allowing the branching program to.
And each time the x1 to xn sequence of vertices and the edges between them are different.
Yeah, they can be different. So it's just a graph. It's an arbitrary graph.
So is there any difference between a three pass three pass branching program and a W and CN signal?
Yeah, because you're reading the same input. X1 to xn, there it would be like x1 to x3n.
Oh,
yeah. Yeah, it's the same input bit you're reading again. Okay, so now we will focus on read once branching programs for the point problem. So here, what do we mean by now? As the question was asked, when we are looking at x1 to xn, these are the coin tosses, and we will represent heads by tails by 0, and then you are given the outcome of the coin tosses, which is the n bit, and then your read once branching program does some computation, and in the end, if it outputs 1, it is saying that like I think it is biased towards heads. If it is saying 0, then we say that I think the read once branching program is claiming that it's biased towards 0. And so this is this is what we want to construct. We want to construct read once branching programs for the coin problem, which says that if the input is generated from this distribution that is biased towards heads, then with high probability it should end in an accept state. And if it was generated by a by bias towards 0, then with high probability it should end in a 0 state. But first, let's look at what is the optimal distinguisher for the coin problem. Like what is the optimal algorithm that achieves the best success probability for distinguishing between the case where it's biased towards heads versus the case where it's biased towards tails. So this is just like without any computational model, this is the optimal function that solves the coin problem, which is you compute the sum, that is in other words, compute the number of heads and compute the number of tails. If the number of heads is greater than number of tails, you say it's biased towards heads. If the number of tails is greater than number of heads, you say it's biased towards tails. So this is the optimal distinguisher, and let's see what is a read once branching program that computes this. So you start from 0. You start from here, which is a start vertex. If you see a 0, you remain in the same. Let me call this. So these are layers. I want a word for this. Row. Okay, yeah. So this is a row. So you stay in the same row if you see a 0, and you go to the next row if you see a 1. And basically, like, now each row represents a sum. So the first row is representing the sum up till now is 0. The second row is representing sum up till now is 1. And the last row is representing sum up till this is n. So then you keep this computation, and then basically all these last n by 2 nodes in the last layer are accept states. So all of them are accept states. Half of them are accept states, half of them are reject states. So this is a advanced branching program that computes the sum, or like computes the majority perfectly. But so what is it? It's width n, and length n branching program. And now this is the question: we want to improve the width. Do we really need n width to solve the coin problem? So then, you can show that if you want to compute it perfectly, like if you want to solve the coin problem like perfectly, then you need n width. Basically, if you want to compute the sum perfectly, then you need log n memory, or n different states, representing each sum. So now the question is, what about 0.9 success probability? That is, you want to be accurate only with 0.9 0.9 probability. That is, if it is biased towards 1. So now the randomness comes in. Now what does success probability mean? If each bit now x1 to xn is biased towards 1 with probability half plus delta, then with probability 0.9, in the end I should reach an accept state. So this is the definition of success probability. Any questions? Yeah. So we will talk about only deterministic branching programs. Yeah. Yeah, and plus this function needs to be computed by a low width advanced branching program. Good. So this works if delta is a constant. So yeah, it's a low weight program. If delta is a constant, we will talk about like delta as a factor of n. Okay. So what is known in the coin problem in ROBPs, advanced branching programs? So exactly. So if delta is 1 by square root n, then at least with n coins, coin tosses, I can statistically distinguish. So the previous advanced branching program that I gave you, if delta was less than 1 by square root n, then it's just impossible to solve it with probability 0.9. But if delta is greater than equal to 1 by square root n, then I can then at least there's an upper bound. So these dots are now representing an upper bound. There is a width n branching program that computes it, that solves the coin problem. So what about like larger biases? Maybe we can do better. So for example, we know that for constant bias, we only need constant width branching programs. In fact, this is already interesting and goes beyond low space algorithms. That is, we can actually detect or solve the coin problem for 1 by polylog n bias with only constant width branching programs. And then now even more surprising is that we can, oh, I did the same thing. So now even more surprising is that you can actually detect like 1 by Polynomial bias with only log n bits branching programs, read-once branching programs. So you would think that at least like 1 by n to the epsilon biases require large n width, but this is true that you can detect like 1 by n to the 0.3 bias with log width. So we will look at the construction for this low width construction for detecting such biases. Now, what about lower bounds? So there are these papers by I think there was a bug in this proof by Steinberg in 2013 that shows that these 2 points are tight. That is, you require approximately log 1 by delta with read-once branching program minus log n factor. That's why you're getting a constant here. In 2020, we proved that if bias is 1 by square root n, then you require n to the omega 1 width, that is polynomial width for read-once branching programs to solve any point problem. Now, but there is still a gap, and in 2021, we showed that there is actually a phase transition that happens at 1 to the n to the minus 1 by 3. That is, if the bias is less than 1 by n to the 0.33, then you require polynomial width for read-once branching program to detect. But if it is larger than this bias, then log n width read-once branching program suffices. So this is pretty surprising because you might have thought that there would be like a smooth transition, but there is actually a phase transition that happens at this bias of n to the minus 1 by 3. So in this talk, we will focus on these upper bounds, we'll start with the construction here and then eventually come to the construction for read-once branching programs for detecting 1 by n to the 0.33 bias. Any questions? No, I don't like. I feel like we came up with this construction, and then somehow this was tight. We proved it. It was not. Yeah. So for the lower bounds, this paper gave an information theoretic proof, whereas this paper. Which as I will discuss in the open problem, which we were able to generalize to multipass, but this paper gave proof which we don't know how to generalize to multipass. Okay, so let's look at upper bound for delta greater than equal to n to the minus 1 by 3. What does this mean? That we know that basically n to the 2 by 3 coin tosses should suffice to distinguish for such biases, but we are given way more than that. We are giving n coin tosses to you for distinguishing between heads and tails with bias delta equal to n to the minus 1 by 3, and the fact that we are giving you more coin tosses is how is this useful to detect with lower width than just keeping a track of the sum. We can do it in log n width read-once branching programs. Okay, so the teaser is this tribes function. Let's start with just read-once Boolean formulas that can solve the coin problem. So what's a tribes function? So the tribes function can it's basically you divide the input into blocks of length m. So there are n by n blocks, and on each of the blocks you take an AND, and then you do an OR of the output of all these ANDs. So pictorially, this is my tribes function. Basically, these are like log n length, and you have n by log n of these ORs, and then you can compute the so this is the tribes function, and the fact is that this tribes function can solve the coin problem for some values of delta. So for constant values of delta, we can just actually compute the sum. But this tribes function can actually solve the coin problem for 1 by log n delta. So what does this mean? When each input bit is biased towards 1 with probability half plus log n, then we can show that there is a constant bias towards 1 on the output of this function. So this means that if so this can be thought of as a bias amplification. That is, like, I'm giving you input bits with bias 1 by log n towards 1, and you're getting an output that is biased with constant bias towards 1. And basically this amplification, with this property, you can also show that basically it can detect biases of 1 by log n. That means that if it was biased towards 0 with this probability, then it will give you output of 0. So that means that you are figuring out, like, whether it's biased towards heads or tails. Questions?
The definition of tribes function imposes log n, or you are choosing a specific parameter for a general definition of tribes?
I guess I'm not sure, but let's say we are choosing log n.
The results vary to choose something significantly from log n.
Yeah, but then it's not interesting because this log n is chosen so that, like, the output is actually, if you're given uniform distribution, then the output is actually balanced, that it's 1 with probability half and 0 with probability half. And we are looking at deviations from uniform distribution, so these are the right parameters to consider. Okay, so now we will see that the fact that we will simulate the tribes function using a read-once branching program of just 3 width. If we wanted to compute the tribes function using our Python or whatever, then we would have, like, some term like for I goes from 1 to n by m, do this. So which is already, there is some memory required, which is like log n bits. But using a non-uniform model of computation, which is the read-once branching program, we can just compute it using 3 width. This is how you do it. So I have each row representing a different thing in this. Okay, so the length is n and the width is 3, and I start with the start vertex, which is colored. What does this represent? This represents that this middle row represents that at this point I am trying to compute the value of the and on this block. If I have moved to green, that means that the value of the and last was 1. If I find a block which has whose and value is 1, then I can just output 1. So I can just accept. So I will remain in this state. And the upper thing represents, the brown row represents that the and value of this block is at least 0. So I need to compute the and value of the next block. So this is m length. So what I do is I start, if I keep receiving 1, that is, like, I still have hope that the and of this block is 1, and I keep on doing this. And if I actually reach a state that and of all of m things is 1, I go to accept. But if at any point I go to 0, I see a 0, I transfer to, like, okay, it's time to wait for the computing the and of the next block. So this is the advantage of a read-once branching program, that my layers can differ depending on what bit I'm reading. So if I'm reading this bit, then all these layers are looking same. But I know that when is the time after m input bits, it's time to transition to the calculation of the next AND block. So this is what is useful in computing that, in finding a 3 constant width or 3 width read-once branching program that solves the point problem for 1 by log n. Question?
After every m block, we are translating double.
No, so so this means that we have seen all ones, and this means that the and was 0. So this state is meaning that I need to compute the AND of this block. So after reading m bits, I have exhausted all the bits for that are going into the first AND. Compute the second AND. So this is meaning that okay, I need to start computing the second AND. Okay. So just using recursive tribes by setting the width of the by setting the recursive tribes parameters rightly, we can say that like this implies a width w length n read-once branching program that detects a bias of 1 by log n. So if you keep, and this is basically tight. The paper by Steinberg shows that maybe it's tight up to like 1 by log square factors, but it's tight. That there for every if you have a W width read-once branching program, you cannot solve the coin problem for biases smaller than 1 by log n to the W. And this fact, just as a side note, this fact is used in like pseudo randomness and stuff. That basically you are saying that a random coin, a biased coin, can fool read-once branching programs. So these kind of techniques also have applications to pseudo randomness. Okay, so coming back to read-once branching program for the coin problem. So till now we have seen that at least for 1 by polylog n bias, we have constant width read-once branching program. Now how do we jump from here to detecting bias of 1 by poly n? So more generally, what we want to do is we want to identify a bias amplifying gadget and recurse. So for example, we identified that tribes is a bias amplifying gadget. By that I mean that it can take in a bit that is biased with 1 by log n towards 1 by log n bias, and it can amplify it to constant bias. So in general, if I give it a bit that is delta biased, then the output would be delta times log n biased. So it's amplifying it. So the bias is becoming log n times the bias that you feed in. So this is a bias amplifying gadget. And then in the recursive tribes, you basically, the proof is showing that like you keep on amplifying it to get log n to the W bias amplification. So this is what we want to do. We want to identify a bias amplifying gadget and recurse. And we want to simultaneously use the fact that read-once branching programs can simulate read-once Boolean formulas using width that is equivalent to the depth. So this is a non-trivial fact. If I think of recursion, if it has d depth, then a common recursion in Python would say that like I have to at least remember something for each depth. So it will require d memory, or in other terms, the blow up in the width would be 2 to the d. But for read-once Boolean formulas, you can actually simulate it with width that is equivalent to the depth, or d plus 1, and not have this exponential blow up. So this is for read-once Boolean formulas, and this is something that we will use for constructing better read-once branching programs for the coin problem. So here, what is the optimal bias amplifying gadget is by Valiant in 1984. This is optimal read-once Boolean formula, and this was proven to be tight by Bopana and some other people. And so here, basically, you take a constant size read-once Boolean formula that amplifies bias from delta to alpha times delta. And actually, the optimal thing is you just take an OR of AND, OR of 2 ANDs, and each of these ANDs have 2 bits. And then you keep on recursing on this to get a read-once Boolean formula that amplifies delta to, so this calculation is not necessary, but I'm just saying that if you're taking a constant size gadget that amplifies by a constant factor, then it is at least easy to see that if when you recurse, you will get a polynomial in n type of amplification, like n to the epsilon. Because you're taking a constant size it's blowing up, is amplifying by a constant factor, and you keep on doing it multiple times, you will get log n depth. So your bias would be alpha to the depth. Yeah. Yeah. Yeah.
We now have n/4 with slightly larger.
Yeah. Yeah. So n/4, and then you keep on doing this, and then yeah. Okay. So okay. So interesting thing to note is that this is the best read once Boolean formula can do. That it can detect, it can solve the coin problem when bias is greater than 1 by n to the 0.3. But with read once branching programs, we can detect even a smaller bias, which is n to the minus 0.33, and in some sense we will start implementing a recursive majority using read once branching programs, which we cannot do using read once Boolean formulas, because majority just takes a lot of. Okay, questions? No, DNFs, no, yeah. So we started with DNF, but when we do recursion, it's a log n depth formula. So this gives us the best amplifying. You can take any other formula and try to see what is the amplification you can get and then recurse. But this gadget, amplifying on this OR of AND, gives you the best amplification possible for. Okay, so let's look at the proof of this fact that read once Boolean formula of depth is simulated by a read once branching program with width d+1. As I mentioned before, a basic recursion would use d memory or 2 to the d width blow up, because as we saw that space d algorithms can be implemented by a 2 to the d width read once branching program. Okay, so this is the idea. So now each row, so again, this is the length, this is the width of the read once branching program. I have not constructed the read once branching program. This is an, so these do not actually represent the nodes of the read once branching program, but this picture is representing that each row in a read once branching program is representing a depth of the read once Boolean formula. So for in every layer, I will have d or d+1 different nodes, and each of those nodes would represent that would represent something about that depth. I'll tell you what it represents. So how do I do a computation on by read once branching program on this formula? So I start with the this is my start vertex. My start vertex is the node in the first layer that represents the lowest depth. So if I see a 0, that means that so this is an OR AND tree. Sorry, I missed that. So this is an OR AND tree, and I want to implement that using read once branching program. And I start with this vertex. If I see a 1, that means that the OR of this, like this form, this small subtree is 1. So I don't even need to read the next bit, because no matter what is the next bit, if this bit is 1, I know that my output of this small subtree would be 1. So how do I represent it using read once branching program? I transfer to the in this transition, basically I will transfer to a node in the representing the depth 2 in the second layer. And if I'm there, that means that I'm not going to read the second bit, or basically like I don't care what is the second bit. And then, okay, so when I'm here, that means that, okay, I can ignore this. So this is somehow reminiscent of the tribe's readvance branching program, where if I was in the top layer, I am ignoring the next bits. So I'm going to ignore this bit, and then when it's time for the third bit, I'm going to come back to the last layer, last row, because I need to read now. Now to compute this this subtree, I need to read this bit. Now let's say I read a 0. Then again I remain here because the value of this OR is not determined yet. It depends on the value of this bit. So again, let's say I read 0, then I can determine the AND of and like the bigger subtree. So okay. So one thing, so what does this represent? If in a layer I am in a node that represents a depth R, that means that I know the answer for the child for the subtree at depth R. The entire subtree, I know the answer. I don't need to read the inputs till I'm within this subtree. I will go back to the last layer when I need to read the input bit for the next for the sibling of this subtree. Does this make sense? So this is what is representing. So just by knowing that at what depth you are at this time step can tell you what next bit you need to read, and somehow that is all you need to compute the value of this readvance branching formula. So again, yeah, this is just some calculation. So yeah, even if I lost you in the middle there, I want to emphasize that the property that is useful here is that at in every layer there is only one node which cares about what is the next bit, which is the last layer. If I'm in the second layer, which is the last row. If I'm in the second row, that means that I don't care about the next bit. If I'm in the third row, it means I don't care about the next bit, and so on. So there is only one row or one node per layer that cares about what is the next input bit. It is 0 or 1, and based on whether it's 0, I'll transition to somewhere else. Based on 1, I'll transition to somewhere else. Now this is the property that we are going to use to construct optimal readvance branching programs. So in this paper, we defined a new concept called effective width of a readvance branching program, where if for every layer for all but E nodes, effective width of a readvance branching program is E. If for all but E nodes, the transition to the next layer is independent of the input bit. So we care about readvance branching programs with effective width 1. That is, for all nodes but one node, the transition is independent of the next input bit. So what is the key observation? The key observation is that when we recurse on readvance branching programs with effective width 1, then the width increases linearly instead of exponentially. Because it's only effective with 1, only at one node we care about what is the next input bit, and if that input bit is an outcome of another readvance branching program, I only need to expand it there. For everything else, I can keep the readvance branching program as same. So basically, during this recursion, width is increasing linearly instead of exponentially. Questions?
What is that the underlying gates just AND and OR? Like for instance, if the gate included parity, would there be a
Yeah, so yeah, good. So that is for readvance Boolean formulas. But here, I guess we can come up with a readvance branching program for parity also, which has this property that the effective width is 1. This is the fact that this is what it differentiates from readvance Boolean formulas and branching programs. In branching programs, we can construct branching programs with effective width 1 so that we get the same property of in recursion width is increasing linearly instead of exponential. So that's why we will see that like we can construct gadgets like majority with effective width 1.
Then it's saying that with each branching program, except now your edges don't have to go to the next layer, they can go to some layer beyond it. Would that be the same?
Yeah. So yeah, so it's yeah. So we also in this paper we define like a skip branching program, which is just like one row, and then you are skipping to future. So that gives you effective width 1. Okay, so how much time do I have? Oh, I'm almost out of time. Okay, let me just mention mention on a high level. What does this construction look like? So let R be a constant. What we will do is we will construct a R to the 3/2 length. Width does not matter because it's just going by definition it will only grow linearly with effective width 1, which has this property that it amplifies bias of delta to square root R times delta. So if you are given R coin tosses, best amplification you can get is square root R because this is the majority, what majority will give you. But allowing a bit more coin tosses, we are giving you up to the 3/2 coin tosses and then getting the same amplification as majority with this additional property that this read-once branching program has effective width 1. And then when I recurse, so this is a bit cumbersome, but the only thing that we care about is that R to the 3/2 length gives us R to the half amplification. So when we recurse, you get n to the 1/3 amplification. Okay. So I wanted to talk a bit about like how do we construct this. It's not that hard. Maybe I'll go over it like in 1 minute. I'll be fast in this. So how we construct with effective width 1, this you can do with any read-once branching program. You take any read-once branching program. So this is a read-once branching program that computes the sum, but it caps it to square root R. So if my sum goes, if the number of zeros become more than square root R or the number of ones become more than square root R, then I just say keep it in the same like square root R sum. And this is a read-once branching program that is also optimal, like up till some constant loss in the success probability. This is the same as like computing the sum. And now to convert it into effective width, what I do is I basically take this layer with square root R rows and I translate it into time. So square root R becomes square root R time. And similarly, like this happens and this becomes R to the 3/2 length. And when I do this, basically only the last row will be, the transition for the last row will depend on the input bit. And I add some new nodes to figure out like basically which, where in time step I have to transition to the last row. So yeah, so this was a bit hazy, but this can be done, and that is why we get like R to the 3/2 length, because we start with the square root R with a read-once branching program, and then we flatten it to get a R to the 3/2. In some sense, I think it's a nice thing that we are basically embedding the state information into time steps instead of width, and that is how we are getting low. And this is how we are using actually the fact that it is a non-uniform model of computation. Okay. So I wanted to briefly mention beyond one pass branching programs. So for the coin problem in constant pass branching programs, the upper bound remains the same. Of course, if we can detect with one pass, with order log and width read-once branching program, then even like 2-pass branching programs can detect those biases. But now the question is, can you do better? So in the recent work, we showed that if again, like for this special case of if delta is like 1 by square root n, that is you are getting optimal coin tosses, then if even for any like let's say 3-pass branching programs, you require polynomial width to solve the coin problem. And this is the so this is a recent work. And then the open problem that I want to say is that like we don't know what is happening in 2-pass branching programs. Maybe we can detect even smaller biases with log and width. We don't know. So it's pretty interesting to see that if this transition that happened in read-once branching programs, is it the same transition for multi-pass branching programs? Okay, yeah, thank you.
Yeah, so any more questions apart from?
Is there a perspective that one can have with peddling games on trees or something like that?
So yeah, so good. So I guess I don't know of the like a completely formal connection, but we do use pebbling games for a lower bound for a read-once branching program. So basically, like we think of it as like your a read-once branching program can be converted into a pebbling upper bound, and then you show a lower bound for a pebbling game, and that translates to read-once branching program. So this has been done in first in like a paper by Braverman et al. For regular read-once branching programs. There they can show optimal bounds, optimal pseudo-randomness bounds using pebbling game, and in our work we use this.
Yeah, so I guess there are no more questions. Yeah, so then we can thank Sumegha again.
Yeah, thank you.
Send it to.
I sent it, I uploaded it.
Yeah, it's talking open, but whom have you emailed it to?
I just uploaded it.
Or you have to upload it somewhere. So, where are the talks uploaded?
In the downloads.
Oh, so do you know what your talk is called?
Title FS24. That's the name of the file.
This one.
I don't.
Did you download them yet? I downloaded it. You sent it to me?
Actually, now I have a separate link with the Google Sheet, which has all these things. So I don't have to log into it together anymore. So. And download it.
It's just
open
written.
it in the-
Yeah, but
Yeah, there should be.
It's just a PDF.
check if it works.
You hold the pen the other way around and maybe more natural.
Sorry?
You hold it like that and maybe more natural.
Ah, okay.
Yeah.
Your mic is working, right?
I hope so.
Okay. Uh, Hi, yeah. So so the next speaker is Ramya. She's a faculty at IMSC Chennai, and yeah, she works in algebraic complexity in general. But yeah, so now she'll be talking about planar arithmetic circuits.
Okay. So I have 30 minutes to convince you that arithmetic circuit lower bounds are hard to prove even under cold temperatures. So it might be easier to cope with colder temperatures than with hardness. Okay. So this is based on joint work with Pratik Shastri. He's a student at IMSC. He's also here in the audience. Okay. So I'm going to talk about planar circuits, arithmetic circuits, planar arithmetic circuits, and some lower bounds. Okay. So what are arithmetic circuits? These are computational models for computing multivariate polynomials. So for most of this talk, we'll try and compute multivariate polynomials over a given field. So you can fix your favorite field. These are directed acyclic graphs. So the leaves are labeled by variables. Okay, so I should look back. X1, X2, so on up to Xn. They may also be labeled by constants from the field. And every internal vertex is labeled either by addition or by multiplication. If it's labeled by an addition, it's going to compute the sum of its children. If it's labeled by multiplication, it's going to compute the product of its children. Okay. So bottom up, you can compute a polynomial. So one of these gates in the circuit is usually called the output gate. And the polynomial computed by this circuit is the polynomial computed at the output gate. For example, this circuit computes a bivariate polynomial, x1 square plus 3x2 plus 2. So this is the model we are going to talk about. So there are two complexity measures that we will be interested in. One is the size of the arithmetic circuit, which is the number of gates in the circuit, the number of arithmetic operations that you need to compute this polynomial. And the other is the depth of the from the leaf to the root. So here this circuit has depth 3. It roughly corresponds to the parallel time required to compute this polynomial. So much of algebraic complexity theory concerns this computational model, which is called arithmetic circuits or algebraic circuits. And the central problem here is to find the polynomial that is hard to be computed by an arithmetic circuit. So what we want to say is you want to find a polynomial such that no matter how you try to draw a DAG, like this is a direct acyclic graph, this polynomial, the number of gates in that circuit would be quite large. Right? So I used small, large, so I have to quantify it. So you want to find a polynomial of not too large degree. So the degree has to be polynomial in the number of variables such that any circuit computing it requires super polynomial size. I also want this polynomial to be explicit. We just don't want to say show existence. So if you give me a monomial, I should be able to tell you what the coefficient is somewhat efficiently. It's a very relaxed notion of efficiency. If you have seen complexity, it is in the class Sharpie/poly. Otherwise, you can be very relaxed about it. So this is the model we are going to be concerned about. And this is the central problem in algebraic complexity theory. Algebraic complexity was defined mostly by Valiant, this model, and then this question was probably posed in the 1970s. And subsequently, we need to see how far we are from achieving this goal. Okay, so that's what we are going to see. Okay. So in 1983, Baur and Strassen, they proved a lower bound that is roughly omega n log n on the size of any fan-in-2 circuit computing this polynomial. So it's x1 to the n plus x2 to the n plus so on plus xn to the n. They showed that any circuit that has fan-in2 and tries to compute this polynomial must have size n log n. So this is barely superlinear. So it's slightly different from the barely superlinear that Madhusudan was talking about. That is n to the 1 plus epsilon. So for us, that will be truly superlinear. Okay. So this is what Baur and Strassen showed. And unfortunately, this is the best lower bound we know till date. Okay. So if you go back to the previous slide, what we want is super polynomial. What we have is barely superlinear. So proving lower bounds are hard. So what do? We don't have a choice. We have to put some restrictions. That's what we'll do. So you restrict the underlying graph to be a tree. So you tie the hands of the circuit and say that no repeated computation is allowed. Now what can you do? Now you can show much better lower bounds, which is quadratic. Okay. Yeah, that's much better for us. So how does someone show something like this? That any formula computing this polynomial must have size quadratic. So there are n variables. Each variable has individual degree n. So if you're trying to compute this via a tree, you will have n leaves labeled x1, n leaves labeled x2, so on. So there are n variables, each labeling n leaves. The size is n square. So that's not a great proof, right? A one-line proof. So what you would expect is a polynomial that has not too large individual degree and yet can get this lower bound. Right? So that's what Chatterjee, Kumar, Shi and Bok showed. They constructed an explicit multilinear polynomial whose total degree is very small, 0.1 n, and they were able to show a quadratic lower bound in the size of any formula computing this polynomial. So the individual degree has gone down. It's a multilinear polynomial, meaning the individual degree is 1, right? And the lower bound is still quadratic. Okay. So now that's the sad state of affairs with circuits. It's slightly better in the case of formula, so you don't have another choice. You have one another parameter, which is the depth. So you can restrict the depth of your circuit and try to show lower bounds. That's what Limaye, Srinivasan and Tamanna showed. So they proved a super polynomial lower bound for constant depth circuits. So I hope some part of that will be covered in Srikant's talk. So this is the current state of the art for lower bounds. So we defined circuits, we saw what size and depth are, and these are the best lower bounds. So you can't expect great things to happen in this talk. It's really bad, sad state of affairs. Okay, so we are going to now restrict our attention to slightly different regime of polynomials, those whose degree is a constant. Okay, it's independent of the number of variables. So if you look at the previous works, the degree was all dependent on the number of variables. It was a function of n, right? Now I don't want that to be true. So in the case of constant degree polynomials, the situation is even worse. So we do not know even an n log n lower bound. So Baur and Strassen's lower bound, the individual degree was n, right? So here you do not know of an explicit polynomial whose degree is constant and the size is n log n, at least n log n. So you don't have a choice, you have to make restrictions. So in the case of formulas, you have near quadratic lower bound. So for any, you can construct an explicit n-variate polynomial whose degree is constant such that any formula computing it has near quadratic size. So it's not quite quadratic, it's near quadratic. But the degree of the polynomial is constant.
Depends on epsilon.
Yes, the degree is a function of epsilon. For every epsilon, there will be a degree delta polynomial. Delta is a function of epsilon. Constant individual degree. Oh, total degree. Yeah. So you have to use, yeah, total degree. So if this is epsilon, then the total degree would be some delta, which is a function of 1 by epsilon. Okay. Okay. So now the next possibility is restrict the depth. For constant depth circuits, we have some good lower bounds when you want to compute constant degree polynomials. So for any constant r, there exists an explicit n-variate polynomial whose total degree is order r, and any depth r circuit requires size n to the 1 plus 1 by r. It's superlinear. Okay, so constant degree polynomials, this is the current state. So we saw some lower bounds, we saw some lower bounds for constant degree. The situation seems to be degrading, right? There is some degradation or increasing hardness when you go from individual degree being a function of n or total degree being a function of n to total degree being constant. Okay, so now the protagonist of this talk. So we are going to talk about planar arithmetic circuits. So these are arithmetic circuits whose underlying graph is planar. You don't allow any edge crossing. So trees are all planar graphs. So every formula is a planar arithmetic circuit, and every planar arithmetic circuit is also an arithmetic circuit. Okay. So it's not hard to observe that you can planarize any circuit. So what we mean by that is if I start with a circuit phi that has some size s and it computes a polynomial f, it has fan in 2, then you can construct another circuit that has size with a quadratic blow up in size but computes the same polynomial. So what you do is you look at an embedding of the original circuit, you look at an edge crossing, you replace every edge crossing with a small gadget which has not too large size, and you will ensure that the polynomials computed are the same. You have to do it slightly carefully. You have to zoom into this pink zone and then embed the gadget so that no other edge crossings interfere with this. But that's some technicality. So a quadratic blow up in size, you can planarize any circuit. So this means that if you show cubic lower bounds for planar arithmetic circuits, you can get superlinear lower bounds for general arithmetic circuits. And in this talk, we will not do any such thing. So this is not a very non-trivial construction or any observation. This is something that has been observed in the case of Boolean circuits. What we just did is that we also observed it works in the case of arithmetic circuits. So Lipton and Tarjan, they proved the planar separator theorem for graphs, if you've seen it. And subsequently, they also noted many applications of the separator theorem. And one of the applications is proving lower bounds for planar Boolean circuits. And they also proved this for read once planar Boolean circuits. This is similar to what Sumegha said. Every variable appears as a leaf only once. But this result was for computing multiple functions. So you can't really say it's quadratic. You're computing n functions and the lower bound is n square. Later on, it was improved to compute an explicit Boolean function. So Turan proved an n log n lower bound for planar Boolean circuits computing an explicit Boolean function. So from n functions, you could get to one function. From read once, Turan was able to generalize it to general Boolean circuits, but the lower bound degraded from n square to n log n. So this is what planar Boolean circuits literature is about. And in this talk, we will see analogous results for arithmetic circuits. This it may not exactly replace Boolean with arithmetic. Some more things will be added. Is that okay? Okay. So I've defined the model, planar arithmetic circuits. I sort of convinced you that proving hardness is going to be hard, so you should not expect much. Okay, so we have to define a hard polynomial. So I have to tell you what is that polynomial such that any planar arithmetic circuit computing it requires large size, whatever large means. Okay. So for that I need to define what a bilinear form is. So a bilinear form is a quadratic polynomial. You have two vectors of variables, x1, x2 to xn and y1, y2 to yn, and A is an n cross n matrix. A bilinear form is a polynomial of the form y transpose ax. So you have a row y vector and then a matrix and then a column x vector. So it's a quadratic polynomial, but it's a special kind of quadratic polynomial where every monomial is of this form yj times xi. So there are no x square, y square terms. There are only these kinds of terms. So it's homogeneous and it is bilinear. So if you stare at this expression, you can see that any bilinear form can be computed by a formula of size order n square. You just open out the sum gates and write it down. There is an order n square size formula computing it. And what we know is that any circuit computing a bilinear form has size omega n. So there are 2n variables, all the variables must appear somewhere in the circuit. Right? So that's the argument. So this is not a great lower bound. And so m is not that good. You would expect the lower bound to be n log n, at least, right? Matching the current state of the art. So you want to construct an explicit bilinear form such that any circuit computing it requires size n log n. So this is open. This actually is a special case of the question that we were trying to see. We initially said we want to construct a constant degree polynomial. Now I'm saying you are not even allowed to compute an arbitrary constant degree polynomial. You have to compute a degree 2 polynomial of this form. Right? So even this is open. So I must tell what explicit means here. So you say a bilinear form is explicit if the entries of this matrix can be efficiently computed. Is that okay? So Nissan and Bigderson did study the arithmetic complexity of computing bilinear forms for some very restricted classes of circuits. We'll probably not have time to discuss. But yeah, if we get there, we'll see. Okay, so I defined planar arithmetic circuits. We defined bilinear forms. So now here's the result. So we want to construct an explicit bilinear form such that any planar circuit computing it has size n log n. Okay, so that's what we are trying to show. So what is this bilinear form? It's a polynomial of the form y transpose mx, where m is a totally regular matrix. So totally regular matrix is one matrix, all of whose submatrices have full rank. Right? All square submatrices have full rank. Over infinite fields, it's easy to see that there are totally regular matrices. So if you take a field that has roughly like at least 2n distinct elements, and every entry of the matrix is 1 by ai minus bj, right? A1 to an and b1 to bn are distinct. Such a matrix is called a Cauchy matrix. And you can show that every submatrix of this matrix has full rank. So over large fields, there are such matrices. So this is an explicit bilinear form. And we'll try and show that any planar arithmetic circuit computing this bilinear form has large size. Large is only n log n. Is that okay? Okay. So for the purpose of this talk, we are going to see a much toned down version of this statement. So I'll define a model called read-once planar circuits, similar to what Sumegha did. So it's a planar circuit where every variable appears exactly once as a leaf. So if x1 appears as a leaf once, it's not allowed to appear elsewhere as a leaf. We'll try and show quadratic lower bound for read-once planar circuits computing a bilinear. This bilinear, right? By transpose mx, m can be any of the totally regular matrices. It's slightly better when you get from non-read ones to read ones. From n log n, you can get to n square. But it's easy to demonstrate this lower bounds. We are going to try and see a proof of this, if the statement is okay. So it's a constant degree polynomial. Right? It's a quadratic lower bound, but for a much restricted class of circuits. Over finite fields, it might be easy to show. I'm not sure about infinite. Yeah, existence is usually easy to show, but I don't want to commit to that statement. Okay, so this works over infinite fields. This matrix, if you have seen before, has a special status in coding theory. So are called MDS matrices, maximally distance separable matrices, because they can generate MDS codes that achieve the singleton bound. So over finite fields, we do not know constructions of explicit totally regular matrices. So these statements work over infinite fields. Okay, so I have 15 minutes. I think I can give you an idea of the proof. Okay, so to prove this statement, so we are going to prove it only for the case of read-once planar circuits. Leave the general planar circuits. Okay, so to show this statement, we'll have to define what is called a bilinear circuit. So if you think about this, these are polynomials whose monomials have the form xi times yj. So if you really want to compute this via a circuit, then you should not compute terms of the form x1 square by 1 square and so on. Maybe you can compute, but they will eventually have to be cancelled before reaching the root, right? Reaching the output gate. So you better not compute them. So a bilinear circuit is a circuit where if you look at any product gate, it has exactly two children. One computes a linear form in the x variables, the other computes a linear form in the y variables. So that's what we'll call a bilinear circuit. And we'll try and prove this theorem using this definition of bilinear circuits. Okay. So the proof is in 2 steps. We'll flash both the steps. The first step is you do an efficient bilinearization for planar circuits. And the second step is, now that you have done efficient bilinearization, you can try and show this lower bound only for bilinear circuits. Yes. Okay. So what is efficient bilinearization? Suppose you start with a planar circuit that computes a bilinear form and it has size S. Then with constant blow up in size, you can construct an equivalent circuit that computes the same polynomial but is also bilinear. That is, it has this property. Every product gate multiplies a linear form in X with a linear form in Y. Okay. So there is only constant blow up in size here. So now you can work with planar read-once bilinear circuits. So you have almost restricted the whole class now. So it should be easier to prove lower bounds. That's the expectation. And in this process, you will not touch read-onceness, meaning if a variable appears once, even after bilinearization, it will appear only once. Okay, so we'll maybe skip step 1 for now, give you a sense of step 2. Step 1 is not that hard if you have seen some circuit constructions like homogenization and so on. Because you are interested only in bilinear terms, you have to maintain the bilinear term at gate and compute things bottom up. Inductively, you can construct, but I'm not going to elaborate on this. This is not what do we have? We have a planar circuit where there are no edge crossings, and it is also bilinear, and it is read-once. And it computes a bilinear form of the form y transpose mx, where m is totally regular. Now I want to argue that such a circuit must have at least n square gates. Right? Okay. So So what we will use is the planar separator theorem. You may have come across this theorem in various places. So what this says is, if you are given a planar graph, then by removing a small number of vertices, you can construct two disjoint subgraphs. You can partition the graph into two disjoint subgraphs. And there is a small separator in this graph, meaning that if there are three parts A, B, and C of the vertices, then there is no path that goes directly from A to B. Every AB path should go via a vertex from the separator. The separator is not too large, meaning if the original graph had V vertices, this has like a root V vertices. And whatever your two partitions are, they are also not too large. So what is stated here is a weighted version of the planar separator theorem. For every vertex, you are given a weight, you assign a weight to every vertex, such that the sum of the weights is at most 1. Then there exists a partition where C is the separator of not too large size, and the sum of the weights of the vertices in A and B is also bounded. And all paths from A to B must pick a vertex from C. So if you want a picture, I think there is some pictures. Yeah, something like this. Looking forward, right? So you are given a circuit, you know it is planar, you know it is bilinear, so you should apply the planar separator theorem. The planar separator theorem will spit out three parts, A, B, C. So C is smaller compared to A and B. And every path from A to B or B to A must go via C. One of these gates is output. It's not clear where the output is. It could be in A, it could be in B, it could be in C. This is just representative. Okay. So you apply the planar separator theorem with appropriate weights. So to prove this, suppose let's assume that the given circuit has very small size, right, little of n square, and apply the separator theorem, then you know that this separator here must have small size, like sublinear, little of n. Right? And it will partition the circuit, underlying circuit, into three parts, the vertices of the underlying circuit into three parts. And the number of inputs in A and B can't be too large, because A and B had small size and you assigned some 1/2 n weight. I'm just assigning some weight. You can ensure that the weight should just be at most 1, sum of the weights. So the number of inputs in A and B can't be too large. Okay. So maybe I should. Okay. So there are three parts A, B, and C. I hope you will remember the picture. So if you look at three parts A, B, and C, A, B, and C together have 2n inputs. They have n x inputs and n y inputs. So either A union C should have at least n/2 x inputs, or B union C should have. Let's assume that A union C has. Okay. So A union C has quite a large number of x inputs. Now of those inputs, some of them may be in C, but only sublinear many of them can be in C because C itself had small size. So you subtract those out. So A has quite some number of x inputs. These numbers don't matter. I mean, they do matter, but you don't have to remember the numbers. So A has some number of x inputs, quite reasonable number of them. The number of inputs in A itself is bounded. So then A has at most some number of y inputs. This means that there are totally 2n ny inputs, of which many of them are in A. So the remaining of them have to be in B. So if you don't remember any of the numbers, what does this say? So A has some number of x inputs and B has some number of y inputs, and there is a lower bound what the sum is. So there are sets x prime and y prime such that x prime and y prime are reasonably large, and all x prime variables are in A and all y prime variables are in B. That's what you get after applying the separator theorem and doing some calculation. So the picture looks something like this. So this was the original circuit. You have A, B, C. So there is this x prime variable sitting inside A and y prime variable sitting inside B of reasonably large size, like n/13 each. So this circuit was originally read once, which means the variables here cannot appear here, like in other parts. And the variables in y prime cannot appear anywhere here. Well, there can be other variables here. So now you need to use this fact that it is read once. So there are some x prime variables, some y prime variables. You set all the other variables to 0. So now what this circuit computes is y prime times y prime transpose some matrix which has picked rows and columns accordingly times some x variables. So it's also computing a bilinear form, that you are just killing some variables by setting it to 0. So it computes some bilinear form, right, where this matrix here is n by 13 cross n by 13, those variables that survive. So your original matrix was totally regular, so this must have full rank. Is there... Okay. So we started with the fact that the circuit had small size. Right? So I have to do a contradiction somewhere. So we will contradict that the rank of M prime cannot be too large. So we'll try and use the fact that all of these paths go via C. There is a small separator. So I will do a 1 minute proof of that. But is it clear, like so far, what is going on? So this actually, if you stare at the proof, you don't need every submatrix to have full rank. You want only n by 13 cross n by 13 submatrices to have full rank. We just over assumed things actually. So this argument works over finite fields also, because we know constructions of matrices where every n by 13 cross n by 13 submatrix is full rank. Okay, so let's try and contradict this in less than a minute. So what is something we did not use? We used read onceness. We did not use bilinearity, we used planarity. So I must use bilinearity in the contradiction. Okay. So what is a bilinear circuit? If you look at a product gate here, it multiplies it has two children. One is a linear polynomial in the x variables, the other is a linear polynomial in the y variables. So let's say that G is some product gate. It could be in any of these partitions. I'm just assuming it's in A. It has two children. Right? So it multiplied a linear polynomial in x with a linear polynomial in y. So all the x prime variables were in A. So this gate can pick it up from itself, but all the y prime variables are in B. So they must have reached this part via C. Right? So A has no y prime variables and there are no direct edges from B to A. So this linear form here on the y prime variables must have come through C. So what does come through mean in math? And this is what it means. So this linear form here must have been expressible as a linear combination of not more than the size of C, many linear forms. So I'm going to hide the proof of this under the carpet, but that's what come through means in math. I presume it's fine. Okay, so now this is not true just about product gates in A, product gates in B, C, all of them have this property. For product gates in B, the argument would be symmetric. It can pick the y prime variables from here, but then the x prime variables must have come from A. Right? So by symmetric argument, you can show that once you kill all the other variables, the rank of the resulting matrix can't be too large compared to the size of the separator. Okay? And the size of the separator, we assumed is little o of n. But we proved that. We showed that the rank of this matrix is at least n by 13, which is a contradiction. So the only thing we assumed was the size of the circuit we started with was small. Okay, so this is somewhat easier because the variables here, right, the x prime variables here don't appear in B because this circuit is read once. If it were read once, then things can appear here, here, and here. So you need some more finer separators or partition lemmas. So this is easier to demonstrate. The argument for general circuits, planar circuits is not too different, but it requires more work because of this issue. Okay, so I am assuming that the proof of this was reasonably okay. And you are convinced that any read once planar circuit computing a bilinear form corresponding to a totally regular or an MDS matrix must have quadratic size. So there are two steps. We didn't see the first step, which is efficient bilinearization. So we just show that bilinearization works for efficient bilinearization works for planar circuits. We already know it works for circuits. It's just that we don't know whether it works for formulas. So if you're looking for an open question, it's not clear how to bilinearize a formula efficiently. Okay, so for the general case, you have to use a very sophisticated version, which is Baur. Okay, so we have some models which we saw, formulas, read once planar circuits, and circuits. Every formula is a planar circuit, every planar circuit is a circuit, every read once planar circuit is also a planar circuit. So as anyone in this room would do, now you have some complexity classes, some lower bounds, you have to do separations. That's how you would go. So some separations here are somewhat easy to show. I'm not going to demonstrate all the separations. Some of them are as simple as saying that if you look at this polynomial x1 to the n plus x2 to the n plus so on plus xn to the n, you can compute it via read once planar circuit. You have to do repeated squaring. So x1 to the n you can compute using a line that has n multiplication gates and so on. So there is an n log n size read once planar circuit for this polynomial, but any formula has quadratic size. But some separations are somewhat involved and not so explicit. They use some concentrators like super concentrators, which I have not talked about. So there are some separations here. Some are explicit, some are non-explicit. Some are as easy as the one-line proof I gave. Some of them are slightly involved. Okay, so I have 3 more things. Okay, so that's pretty much the talk. So there are some questions that are open. So the first thing is, what we tried to show was, okay, so this statement is what we proved here. Any read once planar circuit requires size quadratic. The actual statement, if you get time to read the paper, it would be that any planar circuit computing this totally regular bilinear form has size n log n. So it's not clear if this is tight, meaning we don't have an example of a totally regular matrix such that any planar circuit computing it has size order n log n. There's a matching upper bound. And construction of totally regular matrices over finite fields, I suppose this is a like long-standing open problem in coding theory. So I would not suggest you work on this, but you can still think about it. It has connections to what is called the GM MDS conjecture, the generator matrix MDS conjecture. But you can still go back and read up how something that you stumbled upon in a talk has a connection to coding theory and generator matrices. You can also try and ask, can you improve this lower bound from n log n to something better? Like how far can you improve? There are some barriers to improving this lower bound. So the best you can expect is something like n log square n by log log n. So there are some constructions of super concentrators by Radhakrishnan and limit on how much you can extend the lower bound, which I'm not talking about. So that is pretty much the end of the talk. I have some more.
Yeah, so we don't have time for like maybe like one quick question we can take if there is one. Otherwise, we'll just move to the next talk. Okay, yeah. So there is a question.
Communication. Can that be thought of as some communication? Can that be framed as a communication complexity question or something?
Yeah, it can be in a very special setting where these agents can communicate polynomials.
I see.
It naturally induces a communication kind of game, but it's not the communication kind of game that we think of.
I see.
So you have Alice and Bob and they can communicate arbitrary polynomials.
Thanks.
Yeah, so let's thank Ramya again for the talk and we'll.
This pointer works here.
So yeah, so while we set up, the next speaker is Nitin Saurabh. His work sort of is in both algebraic and Boolean complexity, mostly in query complexity lately. So today he'll be talking about approximate post-Boolean functions. Yeah, he's a faculty at IIT Hyderabad.
Yeah, hello.
Yeah, okay. So Nitin.
Yeah, thanks, Anime, for the introduction. So yeah, let's see how much we can cover. So I'm going to talk about approximate degree composition. Should be. Okay, so let's get started. Great, and I should probably focus it. Yeah, seems to be working. Right, so Boolean functions is what we're going to study in this talk. They are just functions from n-bit Boolean strings to 0, 1, right? And our favorite friend polynomials again make an appearance here, but this time they will be used to represent Boolean function. So every Boolean function can be uniquely represented by a multilinear polynomial over reals. And by representation, I mean, sorry. By representation, I mean that the value of the polynomial is equal to the function value at every point, right? And because we are working over Boolean domains, you can, without loss of generality, assume that it is a multilinear polynomial, right? And complexity measure associated with polynomials is its degree, and degree is the size of the non-zero term, which is largest in its size. Okay, so for example, AND function can be represented by just the product of variables, and OR function is 1 minus product of 1 minus xi. Both of them have degree n, right? So at times we want to not only exactly represent a function, we want to sometimes approximately represent a function. And so we say that a multilinear polynomial epsilon approximates a Boolean function if at every point it is within error epsilon of the Boolean value. So the px minus fx is within epsilon at every point. This was defined by Nissan and Segedi, and approximate degree is the least degree of an epsilon approximating polynomial. So for example, this linear polynomial over 3 variables, this approximates OR on 3 variables within error 1 by 3, whereas in the previous slide I quickly mentioned that OR has full degree n. So over 3 variables it has full degree 3, right? And without loss of generality, we will assume that epsilon is 1 by 3 throughout this talk, which will be denoted by this tilde degree f, right? Oh, great. So why approximate degree? It's of course a natural mathematical notion of approximation. And in the last 3 decades, there's a lot of work that has happened on this, which has led to it becoming a great tool in theoretical computer science. So lower bounds and approximate degree gives you separations in circuit complexity, oracle separations, communication complexity, quantum query complexity, secret sharing schemes, and upper bounds gives you strongest results in learning theory, algorithm design, differential privacy. There's a lot of work here, so I chose not to list them. There is a good survey by Bunn and Thaler, and you should check that out. Right. So let's come to composition now. So composition of 2 functions f and g is just f evaluated on g, and g basically the set of inputs is evaluated at set of disjoint inputs. That's all it is, right? So f composed, sorry, this will get some used to. Right. So f g is fed into f, and each of these g is evaluated at disjoint set of inputs, right? Right. So it's a basic tool in understanding complexity measure. Usually, it is used to separate different complexity measures. For example, degree and sensitivity. You can find a small function for which, say, degree is small, say 2, and sensitivity is large, say 3, and then you can iteratively compose itself with f to show that degree is at most 2 to the d, and sensitivity is at least 3 to the d. And this way you can show a separation between asymptotic separation between degree and sensitivity, right? So that is what it is used for. So main question for this talk is, does approximate degree compose, right? So is the approximate degree of f composed with g is theta of approximate degree f times approximate degree g. Notice that this is easily answered for the degree, the exact representation version. You can prove it yourself, not that hard. Here it's not so clear, right? So that comes to this question, upper bound and the lower bound, right? So upper bound is proving that the approximate degree of f composed with g is at most approximate degree of f times g, right? And the lower bound is proving the same as the lower bound, right? So even the upper bound is not so clear, right? In the exact version, you can just compose 2 polynomials right here, because the outer function is actually expecting Boolean inputs, right? So it's not so clear. So this was established by the usage of robust polynomials in a seminal work of Surstorff, following up on Bowman, Newman, and Rohrich and de Wolf, right? And so what now remains is the easy part, which is to prove that the lower bound holds, right? So let's see what do we know about it. So in the long line of work, it was shown that the approximate degree of OR composed with AND is indeed at least approximate degree of OR times approximate degree of AND. It is again shown for if the outer function, so outer function is F basically, right? Outer function has full approximate degree, then also approximate degree composes. Recently it was shown for when F is the OR function or the symmetric function. When the approximate degree of G, so for the inner function is equal to the signed degree of G, some notion of approximation. And then also the approximate degree composes. And recently we had extended it to if the approximate degree of the outer function is equal to square root of the block sensitivity. And in this talk, I will talk about if one of the two functions is the recursive functions. So this is all we know about approximate degree composition. Okay, great. I think I'm doing good with time. Okay, so I'll slow down a little bit now. Recursive functions, right? So what is a recursive function? It's just a Boolean function on bounded number of variables, and you iteratively compose it a few times, right? So that's the parameter D. So if either of the function, either the outer function or the inner function is of such a form, then we show that the approximate degree composes. So I will use the phrase approximate degree composes for this lower bound. I hope that has been well established by now, right? Up to some polylog loss, that is what the tilde denotes, right? Great. So what is the proof idea? So you show that for any f and g, if you plug in a majority in between, then you can prove a lower bound of degree approximate degree f times approximate degree g, right? And then if you are working with a recursive function, then you can replace the majority with some loss. That's roughly the two steps in this proof, right? Yeah, so let's see, maybe, yeah, so together they will give you that you get some loss, polylog n loss, where n is the arity of the outer function. Okay, great. So let's get into the proof. So the main part is the first part. We will show that. The second part is actually something that that uses Valiant 84 result, which was used in the Sumegha stock also. Great. So let's move to the first part. Right. So how do you prove lower bounds on approximate degree? So the notion of dual polynomials comes from linear programming, and the question that you ask is what is the best approximation you can achieve using degree D polynomials to approximate f, right? So you write it as a primal, right? So minimize epsilon. This is your polynomial, right? And CS are your variables, and every point it is closed within epsilon, right? So you write this primal, and then you write the dual of it, and if the primal is infeasible, right? How can you show that the primal is infeasible? That is, with degree D, you cannot approximate f within epsilon, right? That's what it means that the primal is, think of epsilon as a number in your mind, right? So if primal is infeasible, you have to show a feasible solution for the dual, right? And a feasible solution for the dual is something that looks like this. What it says is that you have a function psi x over Boolean inputs, right? And it has a normalized L1 norm 1. So if you take the absolute value, you can think of it as a distribution over the inputs. It has zero correlation with low degree polynomials. Okay, so in terms of its own representation, it is only supported on high degree monomials, that is D plus 1 and higher. Okay, so that is what it means. In a way, it's showing that it cannot be approximated by degree D polynomial within error epsilon, right? Oops. Right. So rewriting the whole thing, it says that approximate degree of f is strictly greater than d if you can find such a function which has L1 norm 1, has a good correlation with your function, which is strictly greater than epsilon, and zero correlation with every polynomial of low degree. Great. So let's this is going to be important. And now let's get back to the main lemma, which says that the approximate degree of f composed with majority composed with g is at least approximate degree of f and approximate degree of g. The three-line proof idea is you take an approximating polynomial for the composed function. Okay. Using that, you construct an approximating polynomial for the outer function. And in this construction, you use the dual polynomial of the inner function. So let's see this idea for the main result that we want to solve actually, which is instead of going to f composed with majority composed with g, let's try this idea on arbitrary f and g. Let's see what happens. All right. So you start with f composed with g. You have some approximating polynomial p for it, right? You take a dual for the inner function g with some parameters. So here the error is 1 minus epsilon by 2. Okay. With such a dual, you can define two distributions, mu0 and mu1. So mu0 is supported on values where psi takes negative values, sort of a indication of where g should take value 0. Okay. And mu1 is supported on inputs where psi takes positive value. It is again sort of an indication of where g should take value 1. Okay. So you take these two distributions, and what you can show is that this sort of is nearly correct. So expectation with respect to these two distributions of g is either close to 0 or close to 1. Right. So each of these distribution is nearly supported on g inverse 0 or z inverse 1. Okay. So great. Right. So once you have that property of these two distributions, let's see how to make a polynomial for the outer function using these distributions. So suppose q is going to be my polynomial that will approximate the outer function. Okay. So I want to evaluate q at some n bit input z1 to zn. Right. Given that input, I sample inputs from this distribution mu0, mu1 that I have defined. Okay. So the idea is that if mu0 and mu1 were truly supported on z inverse 0 and z inverse 1, if I want to evaluate my outer function at z1 to zn, I can sample these points from z inverse 0 and z inverse 1, plug it into my composed polynomial, right, and evaluate the function value. Right. So that is what you do. You sample these points x1 from mu z1, x2 from mu z2, and so on and so forth, and evaluate it into the average of this of the polynomial over this distribution. Right. What you can show is that degree of this polynomial q after this linear operator has decreased by a factor d. That is because of the dual of g that we are working with. Okay. So I will not go into that. But more importantly, let's look at the approximation, because this is what we are after, right? So how are you approximating your outer function fz minus qz at any point, right? So this by triangle inequality, you can write it as f minus expectation of f composed with g, and this other thing which is expectation of f composed g minus p, right? But p is actually by definition an approximating polynomial for the composed function. So that thing by linearity is anyway bounded by epsilon, right? So what is important is the first term, right? And if you work out a little bit of math, it turns out that this expectation is equivalent to evaluating f at these expected values. So instead of feeding f the true value of z1 to zn, which are Boolean values, what you are feeding is epsilon or 1 minus epsilon, close to these Boolean values, right? And now you don't know how to bound this, right? Because epsilon is think of it as a constant. So instead of truly feeding in the Boolean inputs, you are feeding something which is within bounded distance from this Boolean input, right? And this f evaluated at such an input can be really far from f z. One particular example is OR. Okay, OR function at all zeros input deviates much faster. Great, but then what you can use is the fact that f is a Boolean function. It is represented by a multilinear polynomial, right? So it is known to be robust till error 1 by n. Okay, so a multilinear polynomial can handle an error of 1 by n and its input. You can you can plug in instead of Boolean values, you can plug in real values which are 1 over n distance to the Boolean values, and then the output will be close to the Boolean output. Okay, so that's what I mean. It's robust to error 1 by n. So you need to, instead of plugging in the multilinear thing, bounded norm thing, not really. Yeah, okay, let me think of one line answer. Right. So what you are feeding is in epsilon and 1 minus epsilons, which are close to constant close to 0 and 1, and you want them to be 1 by n close to 0 and 1. So what you naturally do is you use majority to boost this to 1 by n, right? So that's it. So you plug in the majority, redefine your linear operator, work out the proof, everything will go through, right? So that's it. Sorry. Great, I'm very good on time. So open problems, yeah, prove the approximate degree composition, right? For arbitrary FNG, probably very hard to know. You should give it a try, right? Approximate degree of F composed with OR. This is still open. So is it at least approximate degree of F times approximate degree of OR? The other way around, approximate degree of OR composed with F. This has been proven using arguments from, let me say, quantum arguments. Okay, so it's not an argument which uses these dual witness and dual polynomials. It's some sort of a reduction. So reproving it using dual polynomials may give us insight into making headway on the second question. And the fourth question, I really don't know. If that is true, then you can solve the approximate degree composition. So I have no idea whether that should be true or not. Questions? Thank you.
Yeah, let's thank Nitin.
In the regime that we are working with, what does the fan-in of majority look like?
Log n.
Log n.
That's why you only lose polylog n.
So then this should just be true by Shasta.
No, no.
Okay.
Let me see what you. So I think that is wrong. That should be approximate degree of F composed with G. Yeah. Otherwise, I can't get the lower bound that I'm after. Yeah. Of course, this is true by Sustov result. Sorry. So the fourth point is wrong. Means it's wrongly written. What I meant over there was approximate degree of F composed with G. Can you remove the majority with a little bit of loss?
Any other question, like one or two maybe? Okay, so otherwise, like, yeah, let's thank Nitin again.
Thank you.
All right, so it's lunchtime and we will aim to be back here by 2 p.m. Lunch is at the same place where you had coffee in the morning. If you missed coffee in the morning, follow the people who had coffee in the morning and find your way.